So yeah, as I mentioned, I'm Juan, and my talk's going to be about functional data structures. Just a quick intro. When I had the idea for this talk, I was mostly just going to go through a few data structures in a functional way. It's going to teach you how they work, their APIs and stuff. But then I realized it's going to be one of those talks where I tell you this thing is cool and look at the API, and you're like, oh yeah, that thing is cool. But then we both go home and we forget about it. So it's going to be more about like what can we learn from implementations of functional data structures. So don't worry too much if the actual structures we use might not seem useful or like not interesting or maybe a little too hard to comprehend. I really want to kind of get the point that uh, functional languages not only give us all the awesome things that we've heard of from today and we'll hear later, they also give us a different way to think about how we structure and work on our data. So just some quick intro on me. I work at Capsule. It's a health tech company and pharmacy here in New York. If you're from here, you might have seen our subway ads for the past few months. Yeah, so for the consumers, we deliver to you medicine to you on the same day with really good customer service, and we don't run out of medications and all that stuff. So next time you're in pain or sick, give us a visit on this website. So the way I learned Elixir and Erlang was that I attended the Recurse Center, which if you're from New York, you might have heard. Recurse Center, like the quickest way to put it is basically 12 weeks to learn or do whatever you want with programming with the goal of getting better at programming. So if you feel like taking 3 months of work and doing that thing you always wanted to do or learning that language or that project you've always had in your mind, just apply through the website. It's really a life-changing experience. So my functional education began with the Structure and Interpretation of Kuhner Programs book. It's a pretty well-known book. It's one of those programming books people that haven't read it like to tell other people to read it. So I have read it, so that means I can't tell you to read it. I have lost that ability. But especially chapter 2, what the chapter starts talking about is basically how to represent data. And they represent a pair of items with just pure functions. And this is going to be like the scheme interpretation. I'll give the Elixir one afterwards. So this is the constructor for a pair of items. You can think of a pair as a two-element tuple, x and y, and they construct this data just out of just functions, no actual list or pair or array data structure. The way they do this is that the constructor function returns a new anonymous function that takes another function m and operates on x and y with that m. So the way the pair is actually represented is not like a thing, but it's literally just the action of acting on those two data values. So for example, to get the first item of the pair, you will they call it a car, as it's in Lisp tradition, and what you do is you pass a pair z, a function that returns its first argument. So z in this case will be what's returned by const. So you're passing const a function that will be the m up there, and what this function does, it just returns its first argument. So they kind of opened up the idea that you can represent data and work on it without having technically just using closures and not actually storing anything in memory. You could probably use better names for these variables, but then it wouldn't be functional programming if they weren't just single letter. So it's just the Elixir translation and maybe a little bit easier to read. Then it's just basically the representation for a pair is just a thing that's awaiting an action on the items on the pair. So this wasn't exactly like too complex to understand for me at the time, but when it kind of, and this is the proof that it actually works. So yeah, it returns a function and you call that the car on the function, and then it gives you 1. Okay, so it kind of taught me two things. It taught me that you can use just pure functions to represent pretty complex data, because you can nest these pairs as much as you want to, and you can do like a map filter with just those that representation of pairs. And also, more importantly, is that functional programming gives us tools to solve problems differently. So it's not just about making it easier to work with data because you're not mutating it. It's not just about like functional programming makes parallelization easier. That's awesome, but it also is a different way to think through the problems and data that you're using. So I just kind of want to give you a quick tour to some things that I've learned, what kind of research in this topic. So first list. In Erlang Elixir, we love using lists. We'll use lists all the time. But they're not, if you read the documentation in Elixir for the plus plus operator, it will tell you that if you're trying to append a lot of things where the result of the appends are on the left side, it's not very performant because you're using up a lot of memory to hold that result on the left side. So for this kind of like the representation of that, if you just keep appending on the left side, it'll be very slow and it'll take up a lot of memory. The reason for this is because when you pattern match those long append operations, you're basically walking down a tree of expressions until you find an actual list or item you can pattern match on. And if you have a very large amount of operations and nested appending, it can take a long time, computationally speaking, to find that exact value you want to pattern match on. So this one's not too bad. It's just 3 from the root, but you can imagine like you have to do that for all of them until you finish. But you can actually represent lists as, again, a function, which will be the partial application of appending a list. And I'll show you with some code what I mean by this. And the point of this is you will replace those appends with function composition, which actually ends up being a lot faster and more efficient. And this kind of data structure is called difference lists. They're not very popular. I've only found one place on the internet that talks about them. But I thought that they were pretty cool, so I just wanted to share them. So the way you make a difference list is that you construct them from a real Elixir list, and all you do is you return a function that takes another list and appends it to the first one. And then to turn something into a real list that you can actually use or print, all you do is you pass that return function an empty list. So basically you will be appending an existing list, an empty list, which just basically is like a no-op. So this might seem really trivial, and why would you do this? But to prove that it actually works, you have an A, we have a 1, 2, 3, and we get a function from the front list, and then we have just a regular list with just 4 on it. I call that B on A, and it gives me a list of 1, 2, 3, 4. What this lets us do is it lets us represent appending as just composition. So here we have 1, 2, 3, and 4, 5, 6, each in their own difference lists, and then we have C, which we call append A and B, and then just again to prove that it works, we make that into a real list, and it gives us 1, 3, 4, 5, 6. The reason why that works is because the first difference list was basically waiting for a B to be applied to it so we can append with the A, and the second difference list was waiting for a C to be applied to it to the B, and you basically just compose those together like you would in regular functional programming. It's a little bit easier to read in an ML language like Haskell. You have a dot operator specifically for composition, but with just 2 lists, it's pretty easy to read in Elixir. And this kind of, I didn't write this, I didn't draw these diagrams. They come from very random paper, someone that can't fit their things on a white square, rectangle. But basically, what I thought was cool about this is that it's not really, doesn't really feel like that much difference. You're basically replacing that plus plus with just composing partially applied plus plus. And because of the way functional languages work, this actually becomes pretty efficient because all you do is just build up that composition until you can get everything in one go at the end. So here I have just a quick benchmark that I used for my implementation of this. You can see doing it a bunch of times. You can see here at the bottom the difference list did a lot more operations in 1 second. Anyway, so the second data structure, what I wanted to talk to you about, that is actually in Erlang, it's queues. So Erlang, if you go on the documentation, they have an implementation for queues that you might have used many times. It's pretty good, and they actually represent queues as a tuple of 2 lists. So the first list here is basically the front portion of the queue, and then the back one is the back portion of the queue reversed. Now that's a pretty interesting difference because once it's reversed, then a lot of regular queue operations become O of 1. Like for example, like adding something to the back of the queue now it just becomes like a regular like prepend on a linked list at the front, which is pretty cheap. So this is something that I thought was pretty cool because it's like built into the language. You know, I'm sure any of you have used it. The queue is not like some theoretical thing, but that little idea of representing it as like two lists and then reversing the second one really gives you a lot of performance gains at a large scale. And this is from the Erlang documentation, kind of like to proving that this is something that people use. Like this comes from a paper by Chris Okazaki, Purely Functional Data Structures, and he's the one that kind of came up with this idea of how to represent a queue. And it's not something that's like only in academia, like it's in a real language. So I thought that was pretty interesting. Something that else is interesting is that if you read the book that Chris Okazaki wrote, in his implementation for a queue, he has this very interesting API for operating on data with his own kind of idea of how API should be written. All the functions are pretty short names, and the ones that do the opposite of others are actually that original function with the letters backwards. So tail will be tail backwards, cons will be snock. So pretty fun to use, but looks like the Erlang people don't use it because they do expose the API, but they call it strange and avoidable. And another lesson that you can learn by from the Erlang queue implementation is that someone actually made a typo in the implementation, and I guess they found out too late because it says here that they try to write tail backwards, but someone misspelled it, and so but you can still use it. So for those writing systems that you can't remove functions, be careful your spelling. So I thought that was a pretty cool implementation of kind of like thinking like, hey, how can we take advantage of lists, like linked lists, like they're all one for some operations. So how can we take advantage of that on like something like a queue or something like a stack where like we can really reap the benefits of what's in the primitives. So the last one I'm going to talk to you about is red-black trees. It's pretty hard to do a full explanation of red-black trees in 8 minutes, but I'll try to do it. Basically, red-black trees are binary trees that balance themselves, and the balancing is important because if you have a binary tree and you keep adding things like bigger and bigger numbers and just add bigger numbers, it basically becomes a linked list. So a lot of the operations will be O of n and take you won't have any benefits from what you will get from a regular binary tree. With a balancing tree like a red-black tree, like the name says, things are balanced, so they are in tree form always. So red-black trees have 3 rules. Each node is either red or black, and no red node has a red child. And the third rule is kind of like what follows from the first 2 rules, that every path from the root to the empty node has the same number of black nodes. So this is kind of like a simple one, but you can see there's always 2 black nodes when you go all the way to the bottom. This makes a lot of traversing and finding things really fast. But the real point I want to kind of drive home with red-black trees is that when you want to, they were not officially implemented in a functional language. They're actually implemented in imperative languages, and you might have seen some in like Java or C#. The problem with doing trees in imperative languages is that they don't have tail recursion for the most part, and you got to do a lot of defensive programming to sort of like avoid the invalid states. So you see, especially with C and C++, a lot of like a mess of pointers and like trying to keep all the nodes in the tree, like the things is the way they're supposed to be. And I've tried to write some in a imperative language, and it's like you are able to do it. People have been doing it, but it's not like it's something like you have to. It's tough. Whereas at least with Chris Okazaki, his implementation of red-black T fits in like about 3/4 of a page, a little longer with it's about a page in Elixir. So, and I thought his solution kind of drives home a lot of the points I'm trying to make with this talk. So you have an insert function, and it takes a tree and a value, and it actually calls a helper function called ins, which I'll explain later, that basically returns like a tree, and then it returns that tree, and it puts the color of that tree as black. The new children have I think almost always black, and after the balancing is done. So the way the ins function does is on the empty case, it just returns a new red child with left and right empty. So the first item in the struct is the color. The second and the last one are like the left and right trees, and then the middle one's the value. So the ones that actually inserts not empty values, and I am taking some liberties with Elixir syntax here just to save space. So it should be like color, colon, color, or left, colon, left, but you guys understand that. So it's kind of like a regular binary tree insert where you look at the value of the what you're trying to insert and what's already there. And if it's bigger, you put it on the right. If it's less, you put it on the left, and then if not, you return the tree that's already there. So this is very interesting right now because it's just like the regular binary tree you might do at school, right? Just using recursion. What's interesting is the way the balancing functions does. So basically, the balancing functions, its job is to take illegal states through pattern matching and turn them into legal states. And I thought this was a really good approach that I think a lot of Elixir libraries already do. Like a lot of the way that you use plug, maybe it's a little bit of a stretch, but a lot of the ways you may use plug in the connections track is that you pattern match on like 404s or like 400 any 400s or 300s or like anything that you don't like, and you try to turn that into something you can actually return. And I thought this approach, all the way back when this book was written, is kind of mirrors the way we think about how to handle errors in functional languages. So there's the actual balance function is actually that doesn't have any body inside of it. It's just pattern matching 4 things and returning the same for all. So this is just 4 legal states, which if you remember the rules is that no red node can have a red child. So this is, for example, an example of an illegal state because there's a red under a red, and this is just another one and the other one and one more, and it turns them all into one valid one, which is a red node with 2 black children nodes and all the values in the right places. So I'm sure like for Chris Okazaki, when he was writing this implementation, actually coming up with like what this right value should be probably was a lot of hard work, and it's probably not something that's trivial when you're writing your application, but I think it's good. It's kind of a good lesson to think about, hey, can we skip like a lot of error handling altogether and kind of think like, how can we make the legal states like impossible to happen, because we pattern match on them, we know what they are, we have set out our specification, and we're just going to turn them into like a valid state that we like and can use. So I thought that because of not only because of pattern matching, because we can use recursion, and because we don't have to worry about mutating like our nodes or state, the functional solution is a lot simpler and easier to understand. And basically, to summarize my talk, I think Elixir as a functional language is not just a better tool for your servers or for your APIs or for your embedded system. It's really a opportunity for you to see data and problems differently. And Elixir is a good language to do that because it's pretty forgiving. If you don't want to be all functional stuff, like no one's forcing you to. You can get pretty far with sort of imperative functions, imperative like code. Elixir won't punish you, maybe like other functional languages that require you to know a lot of like background information to even start using them. So I think, but at the same time, Elixir gives you the full power of functional programming should you want to understand it. And so I hope that this talk has kind of piqued your interest in functional solutions to common problems. And I think, yeah, and then some resources. The book Purely Functional Data Structures. This is also a book people tell you to read that they haven't read. But most people that refuse to read it don't know that books are separated by chapters that are independent. You only have to read the ones that are interesting to you. So I only read, like, for this talk, I only read like 3 chapters. A lot of chapters are things you can't even do in Elixir without a lot of hard work. But there are a lot of interesting chapters that are just like, hey, here are these data structures that people do in C or C++ that are really hard. In a functional language, these are really easy. So it's not as hard of a book as people say. And I did write a difference list implementation. It's on Hex. So that's that. And the last one is by Matt Might. He's a famous, pretty well-known programmer. He wrote a good implementation of right-like trees in Racket, which is a Lisp with the deletion function, which is not in the original Okazaki implementation. So some cool resources. And if you have any other questions for me, maybe now or later, I can kind of point you in the right directions if you want to learn more about this. But otherwise, that's it. Thank you very much.